Good morning, dear students. My name is Ferhan Mazher, and the subject today we are studying is Cambridge O Levels Physics 5054. Today we have set our hearts to solve a paper 4 of this subject. We call this alternative to practical. Today we have selected May-June 2024 4-2 paper. This paper 4 belongs from the variant 2, or you can say zone 2. In this video, I am going to present you the solution of this paper to the best of my knowledge and my. So on your screen, May-June 2024 4-2 paper is showing up. The time allowed for this paper is 1 hour, and the total marks for this paper are 40. There are approximately 4 questions. So let's start from the question number 1. Okay, he says a student investigates the resistance of a diode when different currents flows through it. The student sets up the circuit shown in the figure 1.1. So here we have a power source, here we have an ammeter, here you have a diode, here you have a fixed resistor, here you have a switch. The student connects a voltmeter into the circuit to measure the potential difference across the diode. On the figure 1.1, draw the symbol for a voltmeter connected to measure the potential difference across the diode. So, whenever we want to measure the potential difference across any equipment, we connect the voltmeter parallel to that appliance. So, we will connect our voltmeter parallel to the diode. So, here we go. I hope you can see this. So the internet, something happened with the internet. So the student uses a connecting lead to connect the terminals X and Y together, closes the switch, records the voltmeter reading V, records the ammeter reading I, open the switch and removes the connecting leads. Figure 1.2 shows the readings on the voltmeter and the ammeter. So then they say record the readings shown in the figure 1.2 in the top row of the table 1.1. So here we have a table which is 1.1. We have to note down here how much is the reading of the voltmeter, what is the reading on the ammeter. So here you have, we will increase the size so you can, okay. So this reading, which is on the voltmeter, is, so this is 1, this is 2, this is 0, this is 1.2, 1.4, sorry, 0.2, 0.4, 0.6, this will be 0.8, and this is 1. So basically this is 0.82. You see the five portions, 1, 2, 3, 4, are representing 0.2. So this is basically 0.81, I think. I hope. Sorry, this is 0.82. Okay. So each small square is basically representing 0.04. 0.04. So the voltmeter reading is 0.82. You see, this is 0.4, 0.8, I mean 0.04, 0.08. So this reading here is 0.82. Okay, now this reading. So the 1 is here, so it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so this is 0.1, 0.2, 0.3, 0.35. So this reading is 0.35. So we will note down these values there. So our answers are 0.82 volt and 0.35 ampere. So we noted them in this table. Okay, now then they say calculate the resistance R of the diode using the equation R is equals to V by I. So they have given us the formula. So we have to calculate, you should understand this, okay? So we have to calculate the, Record your answer in the top row of the table 1.1 to an appropriate number of significant figures. So we have to calculate the value of the R. The R value will be V by I. So use your calculator for calculation. For example, 0.82 divided by 0.35, and that will be 2.34. 2.34. Then in this row is completed. Okay, here we know the resistance, we know the voltmeter reading, but we don't know the current reading. So I will be equals to, from this formula, I will be equals to V by R. So 0.81 divided by 3.7, and that will be 0.22 ampere. Then in this row, we want to find out R. So 0.81 divided by 0.19, and that will give you the reading 4.26. So that will be 4.3. In this row, they have written the answers into significant figures only. Here, they are writing them also into significant figures. So I hope you understand how this is done. Yeah, our answers are right. This is how this is done. Okay. The student connects a 3.3 ohm resistor between the terminal X and Y, closes the switch, records the voltmeter reading V in the table 1.1, records the ammeter reading I in the table 1.1, opens the switch and removes the 3.3 ohm resistor. Repeat this procedure for resistors of 6.8 ohm and 10 ohm. Completing the table 1.1, complete the table 1.1 by inserting the missing values. Okay, so we have already completed this table. Okay, so we are good with it. As the resistance between the terminal X and Y is changed, the current in the circuit changes. Examine the results shown in the table 1.1. Describe how the change is in the current affects the voltage across the diode and the resistance of the diode. Okay, so we have to pay attention to this. So this is the resistance between X and Y, 0 ohm, 3.3 ohm, 6.8 ohm, 10 ohm. And this is the reading on the of the current flowing. So as you are increasing the resistance between the X and Y, the current is basically decreasing. And what is happening with the resistance? The resistance is basically increasing. So voltage across the diode decreases very little when current decreases. So let's have a look at that table again. The voltage is 0.82, 0.82, 0.81, 0.81. You see the voltage has decreased very little. As the resistance, describe how the current describe how the change in the current affects. The voltage across the diode decreases very little when the current decreases, and the resistance of the diode, as the current decreases, the resistance of the diode increases. Let's check it here. As the current is decreasing, the resistance is increasing. As the current is decreasing, the voltage remains unchanged. I hope you understand. As the resistance between the terminal X and Y is changed, the current in the circuit changes. Examine the results shown in the table 1.1. Describe how the change in the current affects. Okay, I hope you understand. This is E part. Now, the next question and the next F part. A student sets up a circuit using the diagram shown in the figure 1.1. The student finds that when the connecting lead is connected across the terminal X and Y, and the switch is closed, the ammeter does not give a reading. The ammeter is not broken. Suggests the error that the student has made while assembling the circuit. You see, they have connected there a diode, and if the direction of the battery is reversed, if the connection of the battery is reversed, for example, if the current conventional current comes from here, this will let the current flow because the diode will be in the forward bias, means the direction of the conventional current and the arrow of this diode is same. So it will let the current flow, so the ammeter will show some reading. But if you reverse the connection of this battery, then what will happen? The current will come from here, and the direction of the conventional current will be opposite to the arrow of this diode. Then we say that the diode is in the backward biased. Then the diode's resistance becomes very high and it do not let the current flow through it. So the ammeter will show zero reading in that case. So their question is, let me go to that question. Yeah, this is that question. Suggest the error that student has made while assembling the circuit. So we think that the connection with the battery might have been reversed, diode might be in the backward bias. So when the diode is in the backward bias, then no current can flow through the diode. So the ammeter will show zero reading. You can look at the marking scheme, question number 1F part. This is our answer. So we are going to the next question, and the next question coming up on your screen is the question number 2. And it says a student investigates the rate of cooling of hot water in a test tube under different conditions. A part, the student arranges a test tube as shown in the figure 2.1. So here we have a stand and here we have a clamp and we are holding a test tube. In this test tube, we will put hot water and then we will note down the cooling of that hot water. Acha. Pours 200 centimeter cube of the cold water into a beaker, pours hot water into the test tube until it is approximately 1/3 full. Lowers the test tube into the beaker of the cold water until the level of the hot water in the test tube is below the level of the cold water in the beaker as shown in the figure 2.2. Place a thermometer into the test tube. Waits for approximately 30 seconds before measuring the temperature and starting a stopwatch. So basically what they have done, they have poured some hot water in this test tube, then they have poured some cold water in this beaker, and they have put that test tube into that beaker, and they have make sure that the level of the water, the hot water in the test tube is lower than the level of the water in the beaker. So this beaker has cold water, this test tube has hot water. Now the temperature will, and after every 30 seconds they are going to note down the temperature after every 30 seconds. The student measures the temperature theta of the hot water in the test tube. The thermometer reading is shown in the figure 2.3. So read the thermometer and record the temperature in the table 2.1 at the time 0. So this is that table. Here we have to note down the time, the temperature, sorry. Okay, so what is this temperature? So this is 71, 72, 73. So I think that temperature is 73. The temperature is 73. Okay. Then so something happened with the internet, unfortunately. The student measures the temperature theta of the hot water every 30 seconds for a further 180 seconds. Readings are shown in the table 2.1. Complete the column headings by adding appropriate units. So the temperature is measured in degree centigrade, the temperature is measured in degree centigrade, the time is measured in seconds. Then he says complete the time column. 0, then 30 seconds, 60 seconds, 90 seconds, 110, 120 seconds, 150 seconds, and 180 seconds. Because they are taking the observation after every 30 seconds. So we will put the time 0 seconds, 30 seconds. The unit of the time is seconds, the unit of the temperature is degree centigrade, the unit of temperature is degree centigrade. Okay. Then they say describe in detail one precaution that the student must take to make sure that the temperature measurements are as accurate as possible. So if you want the temperature, the measurements you are taking to be very accurate, there are some precautions that your line of sight must be perpendicular to the scale of the thermometer to avoid the parallax error. The bulb of the thermometer should not touch the bottom of the test tube. The bulb of the thermometer should not touch the sides of the test tube. So these are some precautions which we must take. Thermometer should not touch base or the side of the test tube. Let's check the answers. So question number 2A part, question number 2B part, question number 2B second part, question number 2C part. You can pause the video if you want more time. Okay, question number 2D part. The student repeats the procedure in the A and the B, but with 200 centimeter cube of the warm water instead of the cold water in the beaker as shown in the figure 2.4. In my first part, in this bigger beaker, they have put cold water. Now they have put warm water here. The test tube has the hot water, but this beaker now contains warm water. In the first portion, that beaker has cold water. This is the change they have brought. Okay. The students' readings with the warm water are shown in the table 2.1. One of the students' readings for the warm water recorded in the table 2.1 is anomalous. Anomalous means it is out of the pattern. Identify the anomalous temperature readings and explain how you decided that the reading is anomalous. So if you look at that table, so the temperature at the start is 75, then it becomes 68, then it becomes 63, the temperature is dropping, then it becomes 58, then it becomes 55, then it becomes 35. All of a sudden from 55 it comes to 35, and then it goes back to 52. So basically this number 35, that is anomalous reading. That temperature is, I think is a mistake. And why this is mistake? Because the temperature dropped and then it increased. The reading, the temperature following this is more than this temperature. So that cannot be possible. This is not possible, sir. So this 35 is anomalous. Let me read you my answer. 35 degrees centigrade at 150 second. That is anomalous reading. Anomalous is that reading which is wrong, which is not correct. The reading 35 degrees centigrade is much smaller than the reading which is 52 degrees centigrade following it. You see the temperature of the water is dropping. So if the temperature has reached 35, then it cannot go to 52. because the water is cooling. So that's why this 35 reading is wrong. Okay, then let's have a look at the marking scheme. So you can look at the marking scheme. Okay, what they say? He says use the temperature readings in the table 2.1 to calculate the temperature decrease of the hot water in the test tube after cooling for 180 seconds in both the beaker of the cold and the beaker of the warm water. Okay. So this is the beaker for the cold water. Its initial temperature is, I think, 73. And after 180 seconds, it is 34. And this is that test tube which is in the warm water. Its initial temperature is 75 and the final temperature is 52 after 180 seconds. So this temperature dropped from 73 to 34 in 180 seconds. This temperature dropped from 75 to 52 in 180 seconds. So the temperature dropped when the test tube was in the cold water, and that is 73 minus 34, 39 degrees centigrade. And the temperature drop when the test tube was in the warm water, that is 75 minus 52, that is 23 degrees centigrade. 39 degrees centigrade and 23 degrees centigrade. Our answers are right. I hope you understand. Sorry for the internet. If something is happening with the internet continuously. He says use your answer in the D second to decide how the temperature of the water in the beaker affects the rate of the cooling of the hot water in the test tube. So we can find the rate of the cooling. So the cooling rate with the cold water is, there is a 39 degrees centigrade temperature drop in 180 seconds. So the rate of the cooling is 39 divided by 180, that is 0.22 degrees centigrade per second. And the cooling rate with the hot water around it is only 23 divided by 180, that is 0.13 degrees centigrade per second. So you see the temperature of the water in the beaker affects the cooling rate. When the temperature of the water in the beaker is less, the rate of cooling is faster. When the temperature of the water in the beaker is higher, the rate of cooling is less. Okay, so write that comment. I have not written here, but you can write here. When the water in the beaker is warm, the rate of the cooling is slow. When the temperature of the water in the beaker is cold and or less temperature, the rate of cooling is faster. So this is the answer, sir. I hope you understand. You can pause the video there. Suggest one improvement to the experiment procedure described in A and B that allows a more valid comparison to be made between the two rates of the cooling. For a valid comparison, you know the initial temperature in both the cases was not same. The temperature of the water in the test tube, which was surrounded by the cold water, its initial temperature was 73. And the initial temperature of the water, which was surrounded by the warm water, its initial temperature was 75. So the initial temperature of both the waters must be same. Then it will be a good comparison. In both experiments, initial temperatures should be same. Question number 3 on your screen. A student investigates the balancing of a meter rule which has a load of mass m fixed to it at the 5 centimeter mark. So here at 5 centimeter mark, we have a mass amortized. The student places a pivot under the 50 centimeter mark of the rule. Place another load of mass 50 gram on the rule. Adjust the position of the load with the mass 50 gram until the rule is also close to balanced as possible as shown in the. So they move this mass forward, backward carefully, and they stop this somewhere when this rule becomes balanced. So this scale is basically 100 centimeter long. So this pivot is at the 50 centimeter mark. This is fixed. They are moving only this mass until they are able to balance it. Okay. Figure 3.2 shows the position of the 50 gram mass when the rule is balanced. So first part, take the reading from the rule and use them to determine the position of the center of the 50 gram mass. So this reading here is approximately 93.4, I think. This reading here is 95.9, I think. So I will find the middle of these 2 points. So I think this reading is 95.9 and this reading here is 93.5. You subtract them, you get 2.4. So this diameter is 2.4. So from in the 93.5, I will add the radius, that is 2.4 divided by 2. So you will get 94.7. So the center of this circular mass is at 94.7. 94.7 approximately. What they say? 94.7 is the answer. Okay, they say calculate the distance d from the center of the 50 gram mass to the 50 centimeter mark on the rule. Record your answer on the answer line in the table 3.1 on the page number 12. Okay. So we also have to write this value in this table. The table is here. Okay. So D is basically the distance between this 50 centimeter mark and this. So this is 97 point something and this is 50. So I can find the D very easily. So no problem. The D will be 94.7 minus 50 and that is 44.7. So that D value is 44.7. 44.7 is the right answer, sir. Then they say calculate the value of 1000 divided by D. Record your answer on the answer line in the table 3.1 on the page number 12. So 1000 divided by the value of the D, which is 44.7. So 1000 divided by 44.7, that will be 22.3714, 22.4. 22.4. I will note this value in that next table. So you can see I have noted down these values in that table. So the D value when the mass is 50 is 44.7 and the 100 by D, that is 22.4. Okay. Then it says it is difficult to balance the rule. Exactly describe a technique that the student uses to make sure that the value of the D is as accurate as possible. So because you balancing that rule will be difficult, so move that mass 50 gram mass very slowly. Let's say you are moving it to the right, and when you observe that the scale has started tilting to the right, then move it to the left very slowly. And when you observe that it has started tilting to the left, then move it back to the right very slowly. So between these two positions where it started tilting the scale started tilting to the right, and the position where the scale starts tilting to the left, between them will be there some point on which that scale will be balanced. So that's why, sorry, I went to somewhere else. This is move the mass slowly until rule tilts one way. Adjust again until it just tilts the other way. I just describe you. Okay. So this is how you can find that point where that will be balanced. That rule will be balanced. Let me show you the marking scale. You can pause the video if you want to. Okay. Then they say they have given us this table. We have filled that table. Okay. So we have filled this table. That's good. Okay. Now the question is, on the grid provided in the figure 3.3 on the page 13, plot a graph of the M on the y-axis against the 100 by D on the x-axis. The axes do not need to start from the origin. Okay, so we have to draw. You see, we have to draw the mass on the x-axis. Sorry, plot the graph of M on the, sorry, the mass is on the y-axis and 1000 by D, that is on the x-axis. So in the x-axis, the x values are going from 2.4 to 45.0. And on the y-axis, the readings are going from the 50 gram to 100 gram. So I have to plot these points, and then I have to draw a line of the best fit. Okay, so I took the mass here. I started the y-axis from 40, 50, 60, 70, 80, 90, and 100. So 4 centimeter are representing 10. On the x-axis, I have written 25, 30, 35, 40, 45, 50. I plotted those points. On the x-axis, we have 1000 by D. Here we have the mass. I put those points, then I draw the line of the best fit. So the next question is D, first part. This is calculate the gradient G of your line. Show all working and indicate on the graph the values you use. So I chose this point on the line of the best fit. And this point is basically 26.5, 60. Then I choose this point. This point is 40, 89.5. And I will use these points to find the gradient. The gradient is the rise divided by the run. And let me show you. Okay. So remember, I have taken 2 points on that line, and now I'm going to find the gradient. So 40, 89.5 and 26.5, 60, the gradient will be y2 minus y1 divided by x2 minus x1 according to our mathematics. Rise by run. So that will be 60 minus 89.5 and divided by, in the denominator, we will write 26.5 minus 40. And that is, when you do this calculation, it is 2.19. So the gradient is basically 2.19. They say the gradient will be from 2 to 2.4. Our answer is in that range. Okay, then they say the mass M of the load fixed to the rule can be determined using the equation that M is equal to 22.2 multiplied G. Using your value of the G from the D first part to calculate the mass M of the load fixed to the rule. M is that mass which was on the right side, on the left side, sorry. They have given us the formula to find its value. That's 22.G. G is that gradient. So 22 multiplied 2.19, that is 48.6. So we think the mass, or that the mass which was on the left side is So our answer is right. You can look at the marking scheme here. Then they say, suggest why this method of determining the mass m of the fixed load is unsuitable if a movable load of the mass m 40 gram is used. If you look at this graph, if the mass of of the load is less than 40 gram, let me show you. Then the moment arm should be larger. We have to make it larger. If this mass is less than 40, then this D value becomes very large. The D value becomes more than 50 centimeter. And obviously, if this D value will be more than 50 centimeter, then you will be no more on that scale. If the mass of this block here is less than 40 gram, to balance this whole thing, this D has to be more than 50 centimeter. And you will be off this scale. Scale is only, let me, okay, so here is my answer. When the mass m is 40 gram, the D value will be more than 50 centimeter, which will be beyond the end of the rule. I hope you understand. So here we have the question number 4 showing up on your screen now. Question number 4 is the planning question, a new type of question which has been added since 2023. A student has a converging convex lens and needs to determine its focal length. Plan an experiment that will enable the student to measure an accurate value for the focal length f of the lens. The focal length f of a lens can be calculated using this equation. F is equals to u multiply v divided by u plus v, where u is the distance between an object and the lens. For example, this is the object, this is the lens, so this distance is u. And v is the distance between the focused image. If I have a screen here, then the distance between the lens and the screen when the image is focused and clear and sharp. Figure 4.1 shows some of the apparatus available. Triangular object hole cut into a piece of the cardboard. A lamp is connected to a power supply and can be switched on and off as required with the plan for the write a plan for the experiment. So here you have a sorry. Here you have a lamp, here you have a cardboard, here you have a hole in it, and here you have a converging lens, and this is a table. Here I can put a screen here so the image can be formed on it. In your plan, you should list any additional apparatus needed, draw a diagram of the arrangement of the apparatus, labeling U and V, explain briefly how to do the experiment, and state the steps taken to obtain a sharp focused image. Explain how to use your readings to determine the F. Okay. So one thing, I will put a holder here and put a screen in that holder. And I will put a scale here. With the help of the scale, I will switch on this lamp and I will move this lens forward backward, or maybe the screen forward backward, until I get a sharp clear image of this hole on that screen. Then with the help of that scale, I will note down the reading, the distance between the lens and this card. That will be my U. And I will note down the reading, the length between the lens and the screen when the image is clear, that distance will be V. I will note them in the table. In the table headings, I will have U, V, and then I will calculate the F by using this formula. So I will repeat this experiment by changing the gap between the lens and the card, and then by changing the position of the screen. So I will get different 2, 3 values for the focal length, and then I will take their average. Okay. So let me show you. I have written this. So this is that diagram which they ask us to draw. So here you have your lamp, here that card which has a hole in it, and that is acting like an illuminated object. Here we have a lens, converging lens in a holder. Here we have a screen in a holder. Here we have a scale. There. So with this, the help of this scale, I can measure the distance between the object and the lens, and I can measure the distance between the screen and the lens. The distance between the object and the lens is U. The distance between the screen and the lens is V. So this is the diagram they ask us to draw. We need meter rule to measure U, and okay. We need meter rule to measure U and V. We need a vertical screen in a holder. These are the additional things we need. Place the converging lens, lamp, card, and the screen as shown in the figure. Place a meter rule beside the lamp, lens, and screen. Move the screen and the lens forward and backward until a clear and sharp image of the object hole in the card is formed on the screen. From the meter rule, measure the distance between the card and the lens, and that will be U, distance between the object and the lens, and the distance between the lens and the screen, that will be V, the distance between the image and the lens. Note these values in the table and calculate the value of the focal length by using the formula F is equals to UV divided by the U plus V. Then perform this experiment in to how you can improve this experiment. You should perform this experiment in a darkened room. Objects, cards, and lenses must be at the same height above the bench. To get a sharp image, move screen and lens, move them slowly relative to each other. Repeat this experiment by changing the value of the U. Find the average value of the F. When you will find 2, 3, 4 values of the F, just take their average, and this is how this is done. This is that question. This is that diagram. And this is that question. You can write a better answer. Let me show you the marking scheme. I hope now you have an idea and you are also looking at the marking scheme. You see this is a 1, 2, and 4, and 5, and 6. 6 marks question. This is the planning question. So the marking is showing up on your screen. You can write a better answer. I hope our idea is, our work is just to give you an idea how to write this answer. So we have reached the end of this paper. So my dear students, in this video, in this video, we have presented you the solution of this paper, May-June 2024 Physics 505442 paper. I have tried my best to explain you the concepts. I have tried my best to write them in a better way, but I have also shown you the marking scheme, and I believe that my students can write even better answers. And if you find this video useful and helpful to you, please share the link of this video with your friends, with your class fellows, with your teachers, and post the link of this video on your Facebook, on your WhatsApp group, on your Twitter account, on your LinkedIn. So wherever you will post it, that will help me to promote this channel. Please like this video also. and also subscribe my channel. You see, your support is very important for me to keep on doing this work. So thank you very much, everyone. Have a good day. God bless you all.